Hello, student. Continue the power protection. Uh, in the face-to-face class, we talk about the standard classification of the CTs. As you saw explained in the class, okay, two different classes available. More or less, both of them working the same. One of them is for the relay operation. The other one is for the test operation. Sometimes we need to test some devices. So the T1 is more flexible compared with the C1. There are two integer number. The first one represent the error, which means that the epsilon, can you remember the epsilon? Let me exit from this one. The epsilon, we talk about this one, which was IM over IA, I1, sorry. Uh, Talking about this one, the first integer number, which is here 10, also here 10, and the other one is the voltage at the secondary, which is considered the voltage across the magnetizing, what do we call it, magnetizing branch, which mostly is EM. Okay, so you can call it V or EM, that one is epsilon. So more or less, when the epsilon is given, we know it's related to I1. So if I1, which is the current of the current, the normal current or the fault current given, we can calculate everything. uh, Again, please don't forget and consider that one. uh, when we're talking about this type of definition for the standard of the CT, okay, the current at the transformer, the CT value, which is, for example, is 300 to 5. This 5, which is at the primary side, must be times by 20 to give you the current, the normal current of the system, which is mostly considered. Don't forget, these value are not the real value. These value are the standard value, which the CT is designed based on that one. So you must consider this difference with a real value and the standard value. We're using two different value. We're using real value plus standard value to calculate our required from the equation. So as I mentioned in the class, the CT can become in the classes of the, for example, 300 to 5, which is mostly for the relaying action, or maybe can come in the 300 to 1, which coming for the measuring action. So both of them available. So the primary is 1 or the primary is 5 third. The main difference for these two. Okay. Uh, this is one example we can follow and we can do it for this type of standards. It mentioned consider the city is 600 to 5. So we know the primary, which is 5, the secondary of the city. I'm talking about the city. Okay. In the transformer, in the power transformer, we usually talking about N1, N2 over V1, V2. So we're talking about V1, V2. Here, when we're talking about this one, we're talking about the current. So the N1, N2, don't forget, is N1 over N2, V2 over V2 over, sorry, V1 over V2, V1 over V2 equal I2 over I1, I2 over I1. We should consider this. So the terms of the CT here also in the same way we talk and classes and the transformer here is a CT. So we're talking about the I's. So the N coming in the reverse way. I try to say that one. So the classes of the CT based on the standard is the 10C400. So 10 is the error, which is epsilon. Okay, epsilon is 10%. The voltage at the secondary can reach to the maximum of 400, while these are from standard. So right now, going to the real data, it said if the fault current is 5000 amp, what is the maximum secondary voltage and the maximum burden for the impedance? Okay, so these two are going to calculate by this. Step one, we should using this data. Just I zoom in to see better. So the V is given as a 400, you can see. And then the I, the current is 5 based on the CT primary. then times 20 based on the previous page, which said for calculation the current you should times this one by the 20, which is 100 amp, and epsilon is 10%. So based on the equation, which the Zm, if you can remember this, if you just look at this slide, I have to change it from the side. Okay, no worries. Okay, the Zm is Em over Im, correct? Em over Im. So here V over I times 1 over epsilon, and the epsilon was 1, was Im over I1. So here we try to, when we're talking about the I times epsilon, is I1 times epsilon. So V is Em here, as you can see, as I mentioned in the in past. Here is considered as a Em over Im. So we calculate the Zm as 40 ohm, correct? Okay. Next step is to consider the current. What is the nominal current at the other side, which we use the CT. The first side is 5,000. Are we going to measure the 5,000? No, we're using the CT to reduce the current and then do the other steps, which is relaying, testing, blah, blah, blah. Okay, so 5,000 times 5 over 600 become 41 point something. Okay, this is the current of the primary. So this is I1. Okay, and then the maximum error is 10%. The meaning of that one is when we know I1, okay, when we know I1, we know I2 is 90% of I1. On the other way, 10% is goes to IM. So on the other way, on the other word, we can describe it the maximum error 10%. It means 10% of I1 is IM. So you can see the IM magnetizing current is considered as this value by here. Okay, correct? Finally, maximum secondary voltage. What is the maximum secondary voltage? Secondary voltage is this one. Just look, EM is considered as a secondary voltage. Okay, out. Um, the EM is equal IM times ZM, correct? So the IM is 4.16 and the ZM is given as a 40. So the voltage EM is equal 167. If you times these two, you can reach to the value of 167. Okay, then determine the maximum burden. For the maximum burden, how we can calculate the maximum burden? The maximum burden is coming in a way that we know the voltage EM, which is 167, correct? Oh, sorry, 167. Then the current I1 over IM, which is this one, is I2. So on the other way, the ZB, it said ZB, which is the burden of the impedance, is EM over I2. Just look at the figure I redraw. It's the same as something we expect. So the maximum burden for this system, okay, cannot be exceed 4.45 included ZX2. So don't forget ZX2 also consider inside, included inside this value. Then the Y delta connection, I explained a bit during the class, okay? And I mentioned what's the meaning of that one. Okay, at the left hand side, you can see the current equation related to delta. This is mostly comes for delta. Why for delta? Because for delta, V phase equal V line, correct? Okay, but for the other one, I phase, which is this is coming for the star one, I phase equal I line. So no need to do anything for these two. The only one we should consider is for the star connection or Y connection, we should consider as a V line is equal square 3 times more than V phase when the angle become positive 30. what we call it, I show this one during the class, okay? No, just here I only focus on the current. How I can prove I line is equal square 3 I phase, then the angle is minus 30. Just look, in the case of the delta connection, which is shown by here, in the case of delta connection, we easily know the line current is IA, IB, IC are known, okay? But we cannot start from the line current. We should start from phase current. So here, IAB, IAB, which is the current from A to B. You can see IAB is the phase current. Please consider the difference between the line voltage and phase voltage for the other connection, which is Y. These are a bit confusing, okay? You should memorizing times to time if you review. And of course, since I mentioned, you can memorize this one and keep it in your mind that I phase here is IAB, okay? In the Y, VAB is deciphered as a V line. You see? So be careful about that one. So IA is the line voltage. So we should start it from the phase. Don't forget. Uh, the transformer usually do everything in phase. Then we convert it to line. You can see the voltage in the Y and the current in delta. Okay, so IAB is the reference with the angle of 0 here. Okay, then IBC, then ICA. BC, where is CA? CA is here. So CA with the angle of 120 plus. Okay, positive. This is BC with the angle of minus 120 is given. Okay, now we are going to construct VA, sorry, IA, which is IAB. Let me change it from this page to the other page. IAB minus ICA. Okay, I, which is equal IA. Can you do this one? Means calculate IA by yourself. We know IAB is what? Is IA minus IB, then see IA minus IB, then minus IC, minus minus plus IA equal something. Okay, so I have right now oh sorry, if I leave the minus by here, I have to consider this one still as a minus. Okay, so I have 2IA, which is 2IA minus IB minus IC. Okay, then I can again make this one 2IA. Okay, in the three phase, we know the summation of all voltage or all current equals 0. So IA plus IB plus IC is equal 0. In the same way, we can set VA plus VB plus VC is equal 0, correct? Okay, so here if you look carefully, you can see you can see here is minus IB. I just make IB plus IC, correct? So IB plus IC is equal minus IA, correct? I just using this formula and put it by here. Then I have 3IA, which is the what? Which is the line current, okay? Which is the line current. So based on these equations, you can reach to the point that what is the IA, IB, IC. And then the angle is minus 30. You can see, okay, the IB the IAB is here, then the IA, which ICA minus ICA is exactly by here. The same construction by that one, this one, you reach to this point, which is minus 30, means 30-degree lag from IAB, which is the phase, and this is the line currents. Okay, the phase and the line currents. Then that one is somehow understanding why the current equal this one and how we can decipher. Then in the real connection of the Y delta is happening this way. I have three lines, one, two, three, A, B, C. Okay. Then I have one city on phase A, one city on phase B, one city on phase C. Then the secondary of all cities connected to each other, which is neutral point. This is neutral point. And then the other side is connected to burdens, which this one is the measuring for the phase A, measuring system for phase B. This is for phase A, and this one is for phase C. Okay, and Zn is somehow a resistance to reduce the current between neutral point and ABC, because ABC in the balance condition is zero, but sometimes due some faults it's not zero, so the Zn is there to control that one. This is Y connection. Then the delta connection, you can see, okay, the primary of the first one is connected to the secondary. uh, Assume this is A prime, B prime. So I can say the A prime is connected to B, then B prime connected to C, and C prime you can see is connected to A. So it's make a delta connection. Then the loads, which are one, two, three, are connected here. This is ZF, this one. Then the other ZF on phase B is here, then the other phase. So this is the real connection of the line. But for converting from Y to delta for the voltage, first you have to convert line voltage to phase voltage. Then using the N1, N2 to convert to the other side. Then you have the V phase again at the other side, then convert it to V line. In the same procedure we need to do for the current. So don't forget that one. Zero sequence is a sequence. Okay, in the case of a fault in power system, we cannot use the A, B, C phase anymore. Okay, we have to convert it to another system to analyze. That one is called the positive negative zero sequence. So ABC converted using a matrices converted to positive, negative, and zero. Usually the positive is shown by 1, negative shown by 2, and 0 is shown by 3. Okay, this matrix and this technique is called Fortescue matrix. Okay, Fortescue matrix. This one will be reviewed in the chapter 4, here, and then later in the power system operation and control also unit. You will review it to calculate the fault in the same way. Okay, so this one, the Fortescue matrix, is usually used for the unbalanced fault, which are, we have four different type of fault. Okay, if you review chapter 1 you will see. Okay, single phase means one phase to ground fault. Okay, single phase fault, two line to each other, two line to ground. Okay, these are unbalanced fault. And we have three phase fault, which is considered as a balanced fault. Okay, so in the case of analyzing power system, zero sequence appear only in this type of fault, and it is very important to detect the fault in power system. So there is a special type of connection by the CT, which shown by here, you can see. Okay, this is the way that they connect. Okay, the cities are connected here as a Y, you can see, correct? Okay, then the other side of the city connect on that way, which extract the zero sequence, the Z in the sequence of zero. Okay, so right now it is not an important case for you, because in the chapter 4 We are not going to cover the zero sequence impedance as it is considered by the power system operation and control. So we only focus on the major fault in the power system, which are three-phase fault, okay? Balanced three-phase fault. Then another things about the CT, which is very, very important compared with VT. Okay, in the CT, you should be aware of you cannot leave CT unloaded. If there is a line, if there is a line with a current and the CT is connected here, always the burden must be there. Okay, always the burden must be there. Okay, the ZB. If we remove it due to any problem, if ZB become open, the voltage at this side, okay, the voltage at this side jumps up very high and it's very dangerous. It can be cause of electrocution for the personnel and any engineer. On the case, if anybody going to replace ZB or repair ZB and we cannot turn off this line, we cannot turn it off, means the current is still there, the secondary of CT must be short circuit. Don't forget that one. Okay, next example, which is this example is covering this idea and showing you what is the voltage of this ZB when it is connected to a load, which is the burden, and when the burden is removed. Okay, assume we have a, 13.2 kV feeder. Okay, and the load is 10 megavolt amp in a power factor of 1, which is unity. So cos phi is 1. So the phi is 0. And then the CT is 500 to 5. Okay. And the system is the total load of the CT, the burden, this is the burden. The burden of CT is 10 volt amp. It's a small value, but it's considered for the CT. Then the equivalent circuit of the CT referred to the secondary side, okay, is given at the secondary side, and then calculate the voltage due to opening or accidentally open the CT with or with. Okay, just look at this one. The value given to you. This is what? This is the leakage current, which we considered in the electrical machine as a Z equal. Okay, only the R is given, so the X is ignored because is a was a small value. Okay, so the X is not there, and this is what? This is the parallel branch. This is XM, this is RC. So these two given to you, correct? Then what we know, just look at here, we know the voltage. This is the way of connection, single line diagram of the CT connection. So the voltage, which is a source by here, we don't know where is a source by here, and we have a load. We know the source, which provide the energy for a load. What we know about this one, we know the voltage of the source is for three phase is 13.2 kV. So for the single phase, you can consider it as 13.2 divided by square 3. Okay, then times it by the CT values. Okay, by the CT value. But why the voltage increased by here? Don't forget the CT action is to reduce the current. If it reduce the current, of course it increase the voltage, the same as power transformer in the step down. When we're reducing voltage in the power transformer, we reduce the voltage on behalf of the current increase. You can following this equation N1 over N2 equal V1, V2, V1, V2 equal I2, I1. So this one I think give you the understanding what happened here and why in this example we increase the voltage at this side. Then Z load, which is the load, this one, the load impedance, okay, based on the if you can remember that the system Z, when we calculating the Z was V2 over S, this formula which I use for the per unit, for the transformer, everything is there. So V2, which is 13.2, power of 2, okay, divided by 10. And what is 10? 10 is the load in megawatt is here, 10 megavolt amp. So based on this one, 10 is given by here. So do I need to consider the K for the voltage? When the K become power of 2 become M, correct? So it's K2 over M. So take K2 and M simplified by each other. Then it is moved to the other side of the transformer, okay? Which is CT, okay? We make it in and make it by here. So they move it to this side, okay? Based on this A value, which is N1 over N2, and the final value of impedance of the load is 174.24. Finally, the burden, this burden impedance is given as a 10 volt amp over 5. Okay, what is 5 here? What is 5 here? The S is equal V times I, correct? And then we know the Z, oh, sorry, power of 2. The Z is the same as this formula. I'm going to repeat this formula. The Z is V2, no, I think for here, they're using somehow a different formula to calculate the Z meter value, which is 10 volt amp, 10 volt amp divided by A2. Okay, I think they're using the formula P is equal, what happened? P is equal RI2. Okay, then the Z is given as this one. So the P over I2, so this one is considered as P over I2. Okay, this is the way they calculate the impedance of the burden. So finally, for the V meter, the voltage at the meter side, this is a single line diagram. Again, redraw. You can see the 50, 100. So this one coming from previous. This one is for the burden. This one is for the load, and this is the voltage of the at the CT side. So the voltage over the impedance, we simplify the impedance. 0.4 is in series with this one, again in parallel with this one, again blah blah blah. Okay, you can simplify, but because these values you can ignore it. If you want, you can calculate it in the correct way. Okay, then you can see the voltage finally is something look like this one. So you can following the correct way, which is this one in series parallel with this one, parallel with this one, and then again we have it in series, correct? Okay, or you can following these techniques and said, okay, these two value are big and just ignoring. Okay, for me the first one working better if you can using your calculator, otherwise you should explain why for me. Okay, then this value divided by this one, finally you can reach times, this is voltage deviation, okay, using the voltage deviation technique. Finally, you can reach to the value, the voltage at the meter side when the burden is connected is 175 volt, okay. Then if the burden is not there anymore, okay, so it means that this is not there also, because here become open circuit, because if it's not there, it's an open circuit, so no current will flowing here, all going from here to here. So this one plus a parallel of these two is the answer, you can see. And then suddenly you can see using that one, the voltage jump up to 200. From 1, it's jump up to 200, which is dangerous for human also. So you can see if you leave the CT open, okay, it's quite dangerous for the personnel. Finally, the polarity of the CT. The polarity of the CT is also considered in electrical machine. What's the meaning of that one? If the current goes in from one side of the CT, it must goes out from the other side. If this current goes inside this dot, the other current must goes out from the other dot. Okay, this is the polarity meaning, as simple as this one. Then how we should use this one? Sometimes we make the CT connection in parallel or in series with each other to improve the output current. Look at this one, the figure A, okay? The current goes in the dot. The 5 amp goes in, okay? The CT. And this 5 amp also goes in. So these 5 amps coming, these 5 amp also coming, add to each other, become 10 amp, correct? But for this one, you can see the current goes from this way. So the other way, but this one goes in. I want to say this is the way goes in is 5 amp. This one also coming in this way, opposite of each other, 5 amp. So the total current at this point is 0. So these two CT improve the output. These two CT cancel the current output for each other. Uh, okay, I think the explanation for this one given by here. Right now, I totally covered the chapter 3. Then by another video, I will cover this tutorial question and provide you the solutions. Thank you very much.